So we have some spring problems to consider, and they're all kind of based on second-order differential equations, and it's all about the Newton's law that the force is equal to mass times the acceleration. And then the force can also be described as the spring constant times the offset, and then some resistance. And so we can identify the differential equation. I guess the difficult part about these types of problems is coming up with a differential equation. But once you have the differential equation, it's just the same as solving that we've been doing before. And in this particular case, we have the homogeneous type. And then you'll also be given initial conditions as well to get started. And I think we started to do a problem, and we were just supposed to set it up. But I think there was a slight error in the setup. So let's take a look at that problem that we got started. I think it was number 21. 21, or was it 21? So let's set up the problem. Let's do the problem and see how this goes from beginning to end. It's too big. Let's see. All right, we have a mass weighing 4 pounds, and I guess for these things it's like almost obligatory to draw your spring. With a mass. So the mass is 4 pounds, or the mass weighs 4 pounds, but somehow that needs to be translated. And I think this was our error, is that it needed to be translated into mass, which is in grams or kilograms if we're in the metric system. But if we're in this SI system, then it has to be, it's something like m is equal to, anybody know? Weight divided by gravity. So the actual mass is equal to weight divided by gravity, and the weight is given in pounds and the gravity is given in meters per second squared, and I think that turns out to be a slug. Have you heard of slugs? You come from UCSC, then yeah, banana slugs. So I think that was our error in finding the mass. So just to come back to this equation, we want to fill in these values, the m, the k, the spring constant k, and then the beta, which is some sort of proportion of the velocity that's going to describe our friction, damping. So if the mass weighs 4 pounds, so the weight is 4 pounds, and then the gravity is 32, and I guess they need to look at this going downward and consider the positive gravity. So our mass is going to be, what is it, 4 over 32, which is 1/8. And so this is 1/8 of the slug. Now, depending on how they give you the other piece of information, you may need to do some more substitutions as well. But here they actually give us a spring constant, so that already is going to be K. So K equals the spring constant. and that's equal to 2 pounds per foot. So we have m, we have k, and the only thing we need is beta, which is going to be the coefficient of the velocity. And it says the medium offers a damping force that's equal to the instantaneous velocity, so our beta is going to be 1. Sometimes they say it's 2 times the instantaneous velocity or half the instantaneous velocity, in which case you would put the appropriate beta for that. So our differential equation then would look like this. It would be an eighth times the second derivative. They use x. Should we use x? I guess we should use x. Just know that x is a function of t, and that's what we're looking for. Is equal to, and then so you have to be careful in following this equation properly. And on the other side of the equal sign, these are all negative contributions, so we have to make sure we put that negative sign. So we're going to bring everything over to one side. It'll become positive. So the spring constant k is equal to 2, and that's multiplied by x, the function, and then the beta is 1, and that's multiplied by x prime. So then our differential equation would look like 1/8 x double prime plus x prime and plus 2x equals 0. So now this is a regular differential equation that we've been solving before. Before we begin solving for it, let's take a look at more pieces of information here. The mass is initially released from a point 1 foot above the equilibrium. Oh, that's the other thing, is that we're doing the SI system, right? So everything has to be in feet and pounds. And so if they throw something at us in inches, then we have to make sure we convert. And so in this case, it's all in feet. So that information, or this first piece of information, gives you your initial position. So the initial position for that will give us x sub 0. So I guess here's where we think backwards or upside down. The gravity we're pulling down, and we kind of consider that to be positive. So if it's above the equilibrium point, then we're kind of pushing it back to the negative side. So let's throw a negative sign in front of that. And then it has a downward velocity of 8 feet per second. So our initial velocity is also given, and it's going to be, the down is positive, so we'll call that a positive 8. All right, between the DE and the initial conditions, we have an IVP, so we just solve for this. So let's solve for that, yeah. 5.1. Oh, this part is 5.1. Now that we got the differential equation and initial conditions set up, now it's like back to 4.2 or 4.3. Because this is a homogeneous, so it's easy enough to deal with. Okay, I guess we can try to get rid of the 1/8 if you want, or you can just jump into the quadratic formula. Let's get rid of the 1/8 just so make it a little bit easier, and see what we come up with. So we got the second derivative plus 8 times x prime plus 16x is equal to 0. And is this, you can factor this, right? Is it 4? So it looks like we have a repeated root, and the repeated root is -2. Oh, I'm sorry. I should probably be careful with my notation and what I'm meaning to say. The auxiliary equation is m, so we technically should have gone to m here. M. So m is equal to -2, -4. -4, -2. -4. With multiplicity 2. So we should know our equation then. We should know our what do you call it? Particular general solution. So we have two fundamental solutions for this. This is the second order. We have two fundamental solutions. The first one is e to the -4x. And then the second one is, since it has multiplicity 2, it's itself again. And, you know, by the reduction of order or by some other stuff, we know that we just multiply the next one by x. So from here we get our general solution, and then we'll use our initial conditions to solve for our general solution. So general solution is going to be a C1 e to the -4x plus C2 x e to the -4x. And we use our initial conditions to help us solve for C1 and C2. So in doing so, we need to take, I'm back at y again. Is that bothering you, or do I need to change it? Not change it. just from the beginning, just change it. x1, x2, your solution would be, oh, jeez. So x of t, 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 t. So x is a function of t. Maybe we should write that explicitly. So my variable's t. Instead of x's, I'll use 2. Instead of y's, I'll use x. Or that's what they use. I should have just stuck with y and x, huh? Oh well. The derivative, we need to find the derivative. And so this is, we'll have an extra -4 popping out of this. The next one's a product rule, so we have to be careful. And I'll have C2, I'll put that in parentheses for now, or factor that out, and take the derivative of the first times the second, plus the first times the derivative of the second. So I could simplify this now, but I have initial conditions, so I might as well put 0 in for t to see what gets knocked out. And so that's what we'll do. So initial conditions are put in at this point. We have x of 0. Okay, that doesn't get rid of much, but we can get rid of e to the 0 is just 1, so C1 plus C2 is equal to -1. And our x, what? Oh yeah, because this is 0. So C1 is that. And then x prime of 0 we put 0 in there, we get negative 4c1 plus c2 times 0, and then this part will go away. So this is equal to 8. So we got c1 is equal to negative 1. Put that into the second equation. Positive 4 plus c2 is equal to 8. So c2 is equal to 4. And then you can just finally write your equation, your solution is going to be x of t is equal to negative e to the negative 4t plus 4 t e to the negative 4t. Okay. Any questions? Find the solution. Find the. We still have to find the time. Determine the time which mass passes through the equilibrium position. Find the time which the mass attains its extreme displacement from the equilibrium position, and what is the position of mass at this instant. So for that, I'm just going to graph it and then find some ideal points, the points that they're looking for. First, let me copy this over and put this on a new page. So we have our solution, and let's get our question again and just highlight the things that we're going to need to answer. So, whoops. So equilibrium position, find the time which the mass attains at extreme displacement, and then we can try to figure out if this is, did we figure out, is this critically damped or over damp or under damp? We could have answered that. It's regular damping. We could have answered that when we got the equation in the beginning, the auxiliary equation. So our auxiliary equation gave us one solution, right, of multiplicity 2. So one solution of multiplicity 2 is when the discriminant's equal to 0, so this is critically damped. So it goes and attains some sort of maximum or minimum value where it's farthest away, and so those are some of the things that they're interested in finding. All right, we can graph this using your calculators or graphing calculator or Mathematica or whatever. I'm going to use the graphing calculator program because I think that's easy enough to deal with. And just remember, whatever graphing calculator you have, regardless of what kind of variables you're using, you need to use the appropriate variables for your graphing calculator. So this one uses y for the dependent and x for the independent. So y is equal to e to the negative 4x plus 4x times e to the negative 4x. So this is our graph. It goes up a little bit and comes back down. So we can find those points, find out where the points, where they intersect the x-axis and all that other stuff that they're asking. By tracing, and again, your handheld graphing calculator should be able to help you find zeros and maximums as well. So it looks like the t, the independent variable, is about 1/4. So it's about 1/4 of a second where it reaches our first question. Determine the time in which the mass passes through the equilibrium position. It passes one time in the equilibrium position. A quarter of a second. So I want to copy this. So equilibrium at t is equal to 0.25 seconds. Find the time at which the mass attains its extreme displacement and what is the position of the mass at this time. So let's answer that by finding the maximum. I'm going to take this and see if I can click on the maximum. Here's a maximum at half a second. That's when you get the furthest distance away. Actually, technically, furthest distance away is 1 foot at the starting point. But then after you let it go, it goes as far as 0.135 foot, and then that happens in half a second. So that's the other question. So after the first extreme displacement at 0, it has the next extreme displacement here happens when it's so it happens when t is equal to half a second, 0.5, and then its actual distance, the position, is 0.135 foot. Feet per second. Okay? Is that okay? All right. That's okay. So the next topic is I should have done one of those other one, the undamped one with the sines and cosines, because in the book they discuss a way of putting those sines and cosines into one function. But that's really just that's a trig exercise. So I don't know if they force you to write your answer for the undamped springs. They could potentially ask you to write your answer into one trig function instead of something sine and something cosine. You can combine that into one. But you can look that up. That's just a trig exercise. So the last part of this section is looking at where you have some damping going on, and you also have an external force. So let's take a look at the external force business. So the external force simply adds on a function. So let's say your spring is somehow hooked up to something where it's forcing you to do something, and then you let your spring go and it does whatever it's going to do, and then after a while it's going to start following that external force. So we essentially get a second order linear differential equation with constant coefficients, but now it's non-homogeneous, and we would, again, the hard part is to set up the differential equation, and after that it really just becomes a problem from I don't know, a variation of parameters, or if your external force is one of those easier functions, we could probably do it with a simpler method. What's a simpler method that doesn't have to use the Wronskian and all that? What? No. It's something with the A and B. What's that called? No. No, not Green's. Green's uses the Wronskian and all that stuff, and that's for complicated functions. Undetermined coefficients, I suppose. Not really, but okay. So here they make a little note. Recall that the solution is the sum of the complementary solutions plus a particular solution, and the complementary solution is known as a transient state. And we'll see why it's known as a transient state. And if you haven't noticed, I guess you'll probably notice a little bit more when you start doing homework and stuff. That these we have A and then B and then C in your auxiliary equation. When you do the auxiliary equation, find the what's that called, the quadratic formula. You'll see that your solutions are going to kind of be forced to be an e to a negative power. So whether or not you have whether or not you have sines and cosines involved, as in if you have a trig function involved there, an underdamped, you're going to have your real part of your complex conjugate is going to be a negative, and that's going to give you a solution where you have e to the negative t somewhere in your homogeneous or complementary solution. So the e to the negative was e to the negative t, I think, from way back when, was described as a transient state, because as t goes and gets larger, it's going to go off to 0. So it'll disappear, and then the only thing that will be left dominating is something to do with the external force function. So I'll take a look at that. Is there an example? Let's do an example. Here's a couple of examples. Should we stick with the SI? No, let's stick with the SI. So let's see, we have a mass weighing 16 pounds, stretches a spring 8/3 feet. So unfortunately, in this particular problem, just by reading that first sentence, we're not given our spring constant K, so we have to actually find it. But there's a Hooke's law simple equation that'll help us find that. The mass is initially released from rest at a point 2 feet below the equilibrium position, and a subsequent motion takes place in a medium that offers a damping force that's numerically equal to half the instantaneous velocity. So that's going to be your beta, the constant that's going to be multiplied with the instantaneous velocity. Also, a couple of other phrases or words to look for. Initially released from rest. The idea that it's released from rest means that we're going to do something to the spring and then we're going to let it go. In the last problem, we did something to the spring and then we pushed it initially. That gave us an initial velocity. But when you have something and you let it go, the initial velocity is going to be 0. So that's going to, this from rest business is going to give us another piece of information. Okay, find the equation of motion of the mass driven with the external force of this. So we have an external force. Okay, our our magic equation looks like this. M x double prime is equal to negative k times x minus beta times x prime. But now we have an external force, and that external force is given to us by this function. So we need a few facts. We need 3 constants to figure out. We got 16 pounds for the mass, and again the mass is equal to the weight times the gravity. So this is going to be 16 over 32, which is going to be a half. So that's M. Now here's where we don't have K explicitly given to us, but according to Hooke's law, remember Hooke's law? F equals K times some displacement. So the displacement, here's a story with a spring constant. If you have a spring and the spring has nothing attached to it, then that has its own spring constant. If you attach a force to it, then it's going to get displaced. And so that force with the displacement is going to define our spring constant. So at rest, it doesn't say what the rest is and what the displacement is, or what the new position is, but it gives us a displacement. So this is the actual displacement. So our displacement is going to be the value for S. And then our force is already in force in pounds, and that's going to be the 16. So in our particular problem here, to find our spring constant, we need to set our force equal to 16 is equal to K times, and then our S is equal to 8/3. And that'll help us find our K. So K is equal to, in this case, 6. Nice number. So we got our mass, we got our M, we got our K, and now our beta. What's our beta? So this part is associated with the damping, the velocity slowing down, and so the damping force that is numerically equal to half of the instantaneous velocity. So our damping force takes this and takes your instantaneous velocity, which is x prime, and takes half of that. So our beta is going to be equal to half. Okay. And then we have f of t, so we're ready to set up our differential equation. So our differential equation is going to be, and I'll bring everything to the other side and write the force function, the external force function by itself on the other side. So it'll be 1/2 x double prime. The negative k becomes a positive 6 on the other side. I guess I should do beta first. The negative, and then the 1/2 becomes a positive 1/2 x prime, and then a 6. And then our external force set. So this is our differential equation. X's are all functions of t. So, and to complete this initial value problem, we include our initial position and initial velocity. So our x of 0, your initial conditions, x of 0 is going to be the position, where is it? 2 feet below the equilibrium, and so that going down below business is positive for us, right? So that's 2. And then at rest, says that our initial velocity should be 0. Okay, now we're going to solve for this, and in solving for this, I suppose we could use variation of parameters and the Wronskian and all that, but doing that kind of, it's what is it? It's like using a cannon to kill a fly analogy. Nothing, I suppose. Yeah. Because when they say it's initially released from rest, so we just released it, we don't push it, so there's no initial velocity that we're adding on to this. We're just letting it go. All right, let's solve for this. Let's rewrite our differential equation so that it doesn't have that number in front, and we won't have to deal with fractions. So x double prime plus x prime, and then we got to double the 6, so that's 12. And since we did that, we also have to consider doubling our external force function. Okay, we're ready to go. We're going to look at the auxiliary equation. I'll remember m this time. M squared plus m plus 12 equals 0. Is that nice? 3 and 4? So this is going to be 3 and 4. We got 2 real roots. What kind of solutions are these, or what kind of system is this? Critically damped. So positive? But it's positive, and then I'd solve for it, it becomes negative, right? I skipped a bunch of steps. I don't have the factored form. Right? Oh, one of them is positive. Sorry. Okay. Sorry. Can I factor this? Okay. M plus 4, is that right? M minus 3? So I can't. Okay. Can somebody just tell me what the answer is? So minus 1 plus or minus the square root of 4. White 4. 1 minus 48. 47? Square root of 47? Oh, geez. Over 2. Negative 1/2 plus or minus, so square root of 47 halves times I. All right. So this is our solution, which means we're going to have sines and cosines, and our y1 and y2, or x1 and x2, are complementary solutions. Fundamental solutions, we'll call them, is going to be e to the negative 1/2 t times cosine square root of 47 halves t. And our x2 is going to be e to the negative 1/2 t sine square root of 47 halves t. So those are two fundamental solutions. We can put them together to make our, what do you call it? Our complementary solutions with the C1, C2, but we still need to find a particular solution. So YP XP is by variation of parameters. If my right-hand side looks like this, what should my variation of parameters look like? No, I'm sorry, the other one. Undetermined coefficients look like. A and B and stuff like that, right?
Yeah, I remember doing that.
So if you have a polynomial, then you'll just take that polynomial to the highest degree of that polynomial, and then you have coefficients A, B, C, however far you need to go down. If you have exponentials, then you'll take that exponential with a coefficient out in front. As long as it doesn't match with the other things, then it's fine. So if you have a sine or a cosine, then you need A plus A times sine something, and then B plus cosine something. Do you remember that? All right, you'll have to remember that for the test. So. But was there any in your homework that you had to do trig? Really? All right. Well, you got to do trig. So this is undetermined coefficients. This is our particular solution, or at least the form of our particular solution. What we need to do is we need to take the prime and double prime of that, plug it back into here, and then solve for A and B. Okay? So 3A, what's the derivative of cosine? Negative sine? And 3b, derivative sine is cosine. And we need the second derivative also because our differential equation has is second order. So this would be negative 9a cosine 3t. And this would be negative 9b sine 3t. So we need to put that in our differential equation and then solve for A and B. This looks like it's going to take a little bit longer than 0 minutes, and that's how much time we have left. So what if we just say that you finish this up? I will post a review for the second exam. The second exam will cover chapters 4 and 5, the stuff that we did in class. I did not cover 4.9 and 4.10, and I only covered one section in chapter 5. So those are the exam questions. Oh, I also skipped the annihilator method, 4.7.